In this video, we will look at how we carry out data driven mechanistic modeling. So, given some data on time course of various species involved in a biochemical reaction network and so on, how do you build a mechanistic model maybe based on mass action, Michaelis-Menten or Hill and so on, to accurately predict the time course of various species involved and understand what is happening in the biological network. So, we will look at the various aspects in terms of how we pre-process the data right till how you diagnose the parameter estimates and the fits and so on. How do you solve such complex nonlinear optimization problems? The minima are generally very hard to find because it is in a very complex space. Forget finding global minima, it is worse than a needle in a haystack, right. And there are many strategies. You can do a grid search, you can do various kinds of regression and so on. Gradient descents are difficult because you do not want to be computing the gradient of that function. It is very expensive to compute the gradient of that function. So, gradient descents are again not useful. So, the best algorithms rely on random sampling of parameter space and complex heuristics, and these are usually grouped under what are known as direct search algorithms. You basically directly search in the space. You do not use any fancy gradient computations, any other logic, you just directly search in the space. Of these, the most popular are genetic and evolutionary algorithms. You will maybe study that in one of the coming classes. Grid search is just basically it is how you search for something that you have lost, right. You basically grid the place up and look at every, so it is essentially searching in every place of the parameter space, every section of the parameter space.
So instead of grid search, sampling will be better, right?
Yeah, so you basically divide into grids and do a sampling. So we try to study some sampling algorithms. So you essentially divide the parameter space into grids and you sample uniformly across the grids. There is something called Latin hypercube sampling which does exactly that.
What kind of noise we are using here in biological?
Yeah, again the noise models are interesting, right. So you can have Gaussian noise, you can have Lorentzian noise, it really depends, right, on the system that is being studied, whether it is able to capture the noise characteristics of the system in question. So what is regression or parameter estimation? We know that all mathematical models contain parameters which connect the variables that are being modeled. All of you are very familiar with this classic linear regression, right. So y is alpha a into xi plus some epsilon I residual, right, and you basically minimize the residuals, right. So you do say sigma yi minus alpha xi whole squared and you reduce it and you find the best alpha, right. You may also have an intercept if you want and so on. So regression is the process by which parameters in these kinds of empirical mathematical models are determined using experimental data. This is what we normally call data driven mechanistic modeling, right. That is another common phrase that you will see to describe such models. It is data driven because you are assuming that you have your Michaelis-Menten or whatever some time course data and you also know the mechanisms, right. You do not just make a black box model, just say some alpha x1 plus a beta x2, that kind of thing, right. You know a mechanism, you at least propose mass action equations for that or Hill equations or Michaelis-Menten equations for those exact mechanisms that you assume exist, and then you build a model. And now you have to fit all the parameters in that model back to see if you can regenerate your data. What have we assumed already, right? First thing is, so these are all surprises for most other engineers, right. If you look at a chemical engineer or an electrical engineer, this is a bit of a surprise for them because they usually do not assume a model ahead of time, right, or a mechanism. So in our case, you have A giving B giving C giving D, I am assuming all those are enzymatic reactions, I am already starting off with Vm, Km and all of that for each of those reactions. So you start with 4 reactions, 8 parameters and some known mechanisms, and very tricky in biology, we assume that we have experimental data of sufficient quality, quantity, reliability, precision, whatever. And interestingly, we also have assumed that the model is structurally identifiable. What does that mean? I mean, there are courses that you can do on identifiability and so on, but briefly for our purpose, we will say a model is identifiable if its parameters can be uniquely estimated. You already have a problem here. I can give you a very simplistic example. Suppose you have V is V max into S by Km squared plus S. There is no way you can identify a unique parameter set here, because Km equals 3 millimolar might give you the same behavior as Km equals minus 3 millimolar. You probably know that this is does not make sense, so you can eliminate it, but you have a problem here, right. So, this is a very explicit case. Usually it will be buried so hard that you would never be able to find why your model is not identifiable, what are your issues. So, that is another major problem in biology. It is also more than a problem, you could think of it as a feature of biological data, because there is robustness in biology, right. It is not so tightly fixated at one point that anywhere you move the system breaks, right. The system has some latitude, it has some flexibility to move around in a particular domain retaining its behavior. This becomes a very interesting point, we will come back to it. So, a model is structurally identifiable if its parameters can be uniquely estimated by fitting the model to experimental data, and this is somewhat related to the sensitivity of the outputs to the parameter variations. Typically it means two things: every parameter at least affects say one concentration, and the effects of parameters should also be uncorrelated. If parameter effects were correlated, you can always have high x low y, I mean high k1 low k2 will give you the same behavior as low k1 high k2, and you can never. So, it is like saying other way to look at it is, if this was km1 into km2,
It's only the product that matters.
maybe the product only matters, right. So, those issues will be there, and in fact you will see that very commonly. So, there will be km into 1 plus I by ki, right, for reactions involving inhibition, right. So, maybe this is actually called k apparent. This k apparent might be the most important component rather than km or ki, right. So, these kinds of issues can potentially be there. So, this is a very nice flow chart for mathematical modeling, right. And it will be nice if everybody followed this flow chart in its entirety, but usually we tend to skimp on one or two of the steps at least. So, let us say you start with a data matrix. First thing you need to do is data pre-processing, very often overlooked. Remove collinear points, points that tell you the same thing. For example, one very bad measurement you can imagine is I have so many measurements, these are not informative. What are these points telling you? Nothing. You might as well have had just this point and this point, right. So, these are things that you may want to get rid of.
So, but having them is not going to make a big difference.
Well, you fakely assume that you have more data than you have to estimate your parameters, right. Those are not data points as such. I could it is as good as having 2 points, instead you assume that you have 8 points or 10 points, and then you build a model.
But in large
Do you know the topology? Yeah.
large scale systems, how do you know the redundant, which these data are redundant?
There are ways to check. You can systematically perform some diagnoses on these kinds of models. So, then do you have a model, right, and do you know the topology? Then you try to reduce the model. Maybe we will just build this to building a model, and then you try to decouple, see if there is anything that can be decoupled. Slope estimation is another method to speed up parameter estimation, but basically let us just assume points 4, 5, 6 as the normal modeling exercise that we do, right, and then optimization. Are you able to fetch the data by sticking your parameter set into the model? Does your parameter set help you regenerate the original data? Convergence, great, then you have a candidate model. If no, you have to fiddle around, right. Maybe there are issues. This is the place where it gets tricky. When will you know that your model is not good versus your parameter estimation algorithm is no good? A very open question. There is no clear answer to this, right. So, you may have multiple So, the way we go about it usually is we will start with the parameter space. Let us for simplicity's sake stick to Michaelis-Menten, which means that I will search on a 2-dimensional grid. In a 2-dimensional space I will explore to see is there any point that gives me a good fit to my data. If nothing, I do not know, right. There are two issues, either you did not search hard enough, maybe your domain of search was not good enough, you were looking at the wrong place, or there exists no such point. Maybe in 2 dimensions it is easy to say that, but in higher dimensions it becomes very tricky to say that. Right. So, when do you say that? So, when do you throw your hands up and say, hey, I think my model is wrong, I need to revisit the reactions I have considered, I need to revisit the topology of my model itself. You understand what I mean by topology? The connectivity between different species. Okay. Is A giving B, B giving C, C giving D, does B give C or B give C plus D, or maybe it does not make so much sense in a metabolic system, but in a signaling system this makes a lot of sense. Does something get phosphorylated once or twice or thrice and so on, is there a feedback loop or not? Because one behavior will happen if there is a feedback loop, another behavior will happen if there is no feedback loop. So, how do you handle this? And then hopefully the fun part where we analyze the model and develop our understanding. This is the goal of modeling, right, final goal of modeling. And the other very important thing is this is a cycle, right. You then try to see if you can refine the model, maybe the model is off by a little, can you tweak something in the model or generate new data, perform the one experiment, the one most informative experiment that you needed, right, and try to improve on this. This is again a very tricky part. So, if you see the topology of these 3 models vary, how do you pick the best? Given a model, given a topology, how do you say is this model good or not? This is again an open question, but one way to go about it is you can look at the, let us just consider this is K1, this is K2, and now let me say this is for model 1, this is for model 2, and this is for model 3. Which do you think is a better model?
M3 is worst. That is
M3 is worst, okay, fair enough.
If the model is
We would
high,
normally say that M2 is more biologically plausible,
it's a robust,
because it is somewhat more robust. It admits more changes in parameters without dying, right, without basically failing to reproduce the data, right. So, this can be a measure of, but this is again a very simplified two parameter system. How would you evaluate it many parameters? Here it is very easy, it is just area. In higher dimensions you are going to talk about a very complex volume,
so measure,
right. So, there are many ways, there is in fact some people who fitted ellipsoids in that space and so on. I will share some of those papers. So, you basically, so in a 2-dimensional, let us say this is model 1 and this is model 2, right. So, how do you quantify it, right. So, you may want to fit some shapes inside this and estimate the area. So, now if this area is greater than this area, then you say this is the better model and vice versa. that could be one way to look at it, but you can come up with many more ways. Exactly, right. So if you had a model like this, because what would this mean? What does this mean practically? You have several points where the system is unstable. You move in this direction, you are off. The system does not exist. Whereas here it's very nice. There is a point which is super stable. You have this much leeway to move, right? Whereas here there are some directions where you can move nicely, some directions where you cannot move. There are practical issues, and in higher dimensions this becomes really tricky. But these are some things that one would want to think about. So we were looking at regression schemes. So there are two types of regression schemes. One would be maximum likelihood, and of course you all know least squares. So in maximum likelihood estimation, how we estimate is we try to maximize the likelihood of a parameter set. So you want to find that parameter set that has the maximum likelihood. So the likelihood of a parameter set is equated to what is the probability of getting the experimental data if this were the parameter set for the model, right. So what is the probability of observing your data set given your model and given a parameter set, right. So you then find the most likely parameter values as the parameters that maximize the probability of observing the data. There is essentially a probability value for what is the probability of observing the data given your parameter set, and you want to basically maximize that. So then the parameter set which maximizes that is your best parameter set essentially, right. In least square estimation we basically weight the sum square of residuals, and if the errors are assumed to be normally distributed, this is basically equivalent to maximum likelihood estimation. If you do the math, it comes out as equivalent to maximum likelihood estimation, right. I will not go into the math because you can, it is easy to look this up, this is like in classic textbooks and so on. So one thing that we look for is we assume that the most of the errors that we have in prediction stem from basically the measurement error itself, right. So there are two potential sources. So one is model inadequacy, the other one is measurement noise. We basically assume that model is adequate, right, and we will relegate that to a little later. We first assume that the model is good enough, and then we look at what are your residuals, how bad is your is the fit and so on. So in most regression schemes the measurement errors are considered as the sole source of difference between your data and your model predictions, and model inadequacies are kind of ignored and then relegated to post regression diagnostics, right. Once you perform the parameter estimation regression, you then do some diagnostics, right. One issue with both ML and least square schemes is that they both perform poorly with respect to outliers. One outlier can hurt it. So there are other alternatives possible. You may want to minimize the median of the residuals instead of the sum of the residuals, but anyway you have weighted least square formulations, and there are other noise distributions also that you can use. So all these things become very subjective, right, and they very well depend upon the modeling task in hand and how you pick them and so on. So I hope in this video you got a good overview of how we go about mechanistic modeling given data and what are all the possible steps involved and how would you try and discriminate between good models and so on. In the next video we will start looking at an introduction to stochastic search algorithms or direct search algorithms, and particularly discuss what is the generic recipe underlying practically all direct search algorithms.